Hey guys, welcome back to my channel. So today let's talk about the relationship between expected value of error given x and the expected value of error, conditional expectations of error term and unconditional expectations of error term. Let's get into it. Okay, so let's talk about the relationship between expected value of error given x and expected value of error. Expected value of error given x equals 0. We call this conditional mean 0. This is our first least square assumption for a causal inference. Okay, that means there's no correlation between x and error. So that means there's no correlation between x and error. So actually, if there's no correlation, actually we can write this equation equals a constant. You will see that this is a very strict condition. So it happens when you have randomized control experiment. Briefly, introduction. Okay, that's x is randomly assigned. So you have this y, x. Let's suppose your regression is y test score equals b0 plus b1 x class size and plus error. So x equals 1 is small class and x is 0 large class. And then this is 1, 0, 1. And then if x equals 0, large class, I suppose the test score like this, a smaller, lower, okay? But it's a little bit wider spread out, a little bit more dispersed around the mean. But if x equals 1 is small class, so it's higher score, but a little bit more clustered closely around the mean. So that's heteroscedasticity, or errors are heteroscedastic. So we'll talk about that in the next video, the difference between heteroscedasticity and homoscedasticity. Okay, under what situation errors are heteroscedastic, and in what situation can we have errors homoscedastic? Okay, and if we draw a line through this point, so we get the regression line. Right? And so this term, meaning that if you have randomized control experiment, that means if class size is randomly assigned. So look at the error. Okay, this error is difference between observed value and predicted value. And we know that at this line, you get the expected value of test score given x equals 0. Okay, this point is expected value of error given x equals 1. So any deviation from this point, this mean, is considered as error. So this error includes all other determinants of test score. Let's suppose this other determinants is family income. So that means if you look at this equation, expected value of error, other determinants of test score, given x equals 0. If this equals 0, that means graphically, some of the students higher family income. Some students have lower family income. Some higher, some lower, some higher, some lower. Error is observed value of test score minus predicted value of test score, right? And the difference is error. So this error might, the error, other determinants of what? Some students' incomes are higher, so you have positive. Some students' incomes are lower, get negative. You sum all the errors, and then you get this total equals 0. So that's a randomized control experiment. So just use n or, I. So you sum all the error. Some of them are positive, some of them negative, positive, negative, and that equals 0. Same thing. So we look at the expected value of error, the difference between the observed y and predicted y, given x equals 1. So some of the students in the small class, some of the students, family income is higher, some students are lower, some are higher, some are lower, some error positive, some error negative, positive, negative, and then the average is 0. So if the class size, whether x is 0 or 1 is randomly assigned, so we can make sure that there's no correlation between other determinants of y and x, or the difference in test score that caused by error term is actually has a mean 0 for any given value of x. Right, so this is a very strict condition. So if you have this condition satisfied, and also you have IID, right, and also no extreme outliers, if you have multiple regressors, if there is no multicollinearity, and then you can interpret B1 as a causal effect, unit change in x and y, right? That's what we say. B1 will have a causal interpretation, or you can establish this causal relationship. And what I mentioned in the last video is that if this not true, but this is true, okay, so that's expected value error given x is not 0, is constant, as that is totally fine. That won't bias your
your effect, because you see, you look at it graphically. So let's suppose when expected value of error given x equals 0, the student's family income may be the family income minus mean, right? So that's, some students' family income is higher, some student family income is lower, some student family income is higher, some student family income is lower, but the average is positive. I suppose average positive is A. But you need this is constant. That means equals expected value of this error given x equals 1. So that means you only look at this group. Some students' family income is higher, right, caused by the test score is higher. Some student family income is lower, test score is lower, right? Their error could be positive, negative, but the average is A. So that won't bias your estimate, because you see, you just absorbed by the y-intercept. So this y-intercept b0 actually. That's why most of the time we don't interpret b0, because it's just a placeholder. Okay, so now just y b0 plus b1 x plus error. So if expected value of error given x is not 0, is a constant, and then you find the expected value of y given x equals b0 plus b1x plus expected value error given x is a constant, and this constant is absorbed by b0. So you just increase b0 proportionally. So now this is your regression line. So you won't bias your effect. So b1 can still be interpreted as the causal effect on y of a unit change in x. Okay, so that means in sum, as long as there's no correlation between x and error, as long as there's no correlation between x and error, your b1 will be unbiased. Unbiased means expected value of b1 equals beta 1. So that's the true effect, the true causal effect on y of unit change in x, and this is estimated effect of unit change in x on y. So we're talking about the estimates, OLS estimate here, OLS estimate or OLS estimators. We're not talking about the population regression line. Okay, so yeah, so that's this part. Okay, expected value of error given x basically tells us the relationship or the correlation between other determinants of dependent variable and the most important or variable of interest x. Okay, if that equals a constant, that means there's no relationship. But that equals 0, that happens when you have randomized control experiment. Okay, but for this part, we said that if we ran OLS, it's always equals 0. It always equals 0. This is almost the least discussed, the least talk about subject in the econometric class, because we know that this equals 0, and you should know why this equals 0. So let me give you an example here. So the most intuitive, you can show that mathematically using matrix algebra to show that as long as you have b0 included in your regression, and this expected value error, average of error term, is always equal 0. So as long as you have y-intercept, the mu bar equals 0, we can show that, you can prove that mathematically using matrix algebra. But here, in this video, we are focusing on the intuition behind it. Okay, the example I've given you in my last video is like this. Suppose we just use this regression as an example. So for each observation, you have b0 plus b1, x1 plus mu1. Right? For each observation, we can have this observed value y, predicted value y, right? Plug x2 into the equation, get the estimation error. So if you have n observations, you have n equations. We call this system of equations, right? And then you have this mu n. And now what you can do is you can just add up the right-hand side, left-hand side, get a big equation. So left-hand side add up together, you get the sum y, right? I from 1 to n, right? And this equals n times b0 plus b1 sum x, right? X, I from 1 to n. And the plus sum error, and then I is from 1 to n. And then you divide it by n on both sides. You get this y bar equals b0 plus b1 x bar plus mu bar. Here you get the mathematical expression of mu bar. And the thing is, if this equals 0, it equals 0. But if this equals 1 or 5, equal any constant value, this part, this non-zero component part of mu bar can be absorbed by b0. So as long as you have b0 included in the regression, and the mu bar is always equal to 0. Okay, so this seems like not that important. Again, it's Lisa talk about discussed concept in econometric class. But you need to know that if this is true, we can simplify a lot of calculations. We can simplify a lot of derivations. So mu bar equals 0, you should keep in mind that. And graphically, that means y, x. We have the scatter plot, and you draw a line through these points. So mu bar is actually mu1 plus mu2 plus mu3 plus mu4, all the error term add up together equals 0 or divided by n. So sum error over number of errors equals n. Okay, it's totally different from this given a value of x. Given a value of x would be the error, right? Given the value of x, the error is like this. It could be positive, negative equals 0 or constant. Given the value of x, you have expected value of error given x, right? Whether this equals 0 depends on the relationship between x and error. Right? Whether this equals 0 depends on the relationship between x and error. But this is always true, but this you should think hard. Use your logic, common sense, knowledge about the question to think hard whether there's no correlation between other determinants of y and the variable interest x. Okay, so that's basically the relationship between expected value, expectation of error given x, and expectation of the error term. Okay, hope you find that helpful. Any questions, if you need more detailed interpretation about this, please let me know.